Okay, good morning. Happy New Year to you all. Nice to see you back here. So today we will be talking about an important topic in machine learning, which is probably all the topics that we're talking about are quite important, but this is one which is has a bit more mathematical foundations and is a bit more involved in the mathematics, but it's a very broad field. It's a particular kind of method that we'll be talking about, which helps us to solve problems that are probably hard to solve with direct methods. So variational inference is the topic is called, and the major idea of this topic is to approximate some distributions or approximate problems to make them easier to solve. The motivation of this whole thing is that one major task in probabilistic reasoning methods is to evaluate a posterior distribution of a set of latent variables z given some data x, right? So z is something that we don't know, right? This is some parameters, and we have some data x, and we'd like to know what's the probability of these parameters given our data, which is called the posterior of that. And the problem with that is that very often this is not tractable, right? There's some very hard computation involved in that, and we can't find this very easily with standard methods, right? Not in direct form and not exactly. And now the idea is that we can at least have two different kind of solutions for these kind of very hard problems. One is we can use so-called sampling techniques, right? And these will be handled next week, or in the next lesson. Then we will be talking about sampling. And another one is the so-called variational methods. And today we will talk about the variational methods, which are just another way of approximating these kind of problems here, this kind of posterior estimation problems with mathematical models. Variational optimization generally means that we seek a tractable distribution Q that approximates this posterior. So instead of computing, or instead of working with P, we work with another distribution Q that is very close to that one, but which is much simpler to use, right? So we have some kind of notion about how this Q looks like. We know that Q can be in some way described easier than P, but we also describe it with some kind of parameters, and these parameters need to be adjusted so that Q is very, very close to P. And then we can use Q instead of P for doing the inference. And the whole idea is to use optimization techniques again, and for optimization we always need some kind of objective functions. We need to find a way what to optimize on and how to optimize on, and the whole trick of variational inference methods is to use so-called functionals to optimize this. And the functional is I think I said this already. A functional is is a mapping of functions to real numbers, right? So now instead of having functions itself, which are mappings from real numbers to real numbers, can be in many dimensions. Now we have something that is a mapping from the set of functions to some real numbers. And a very simple functional would be, for example, the entropy. The entropy is simply something that takes a distribution, like P. P is a distribution, and it computes a real number of that distribution, which is called the entropy. I think you might have seen this earlier already. This is just a simple way of a mapping from one space of functions, right, to a real number space. Other things we'll have later are the so-called Kl Divergence. I think we talked about the Kl Divergence already when we talked about EM. Now, in general, this is the reason why we call this variational inference, because variational, this comes from the variational optimization or variational theory, which is kind of an old theory in mathematics. In general, the theory about variational optimization is the theory about functionals, right? How to optimize, how to find functions that optimize a functional, right? Instead of optimizing a function that optimizes that we have an objective function, now we find a whole set of functions, not a parameter, but a function itself that optimizes this functional. Okay, I hope this is kind of clear. This is a slightly different way of looking at it, because now we are in a slightly different space, right? Now we're in the space of functions. We'll see later where the differences are here. So yeah, so the main aim here, as I said this already, is mostly that we would like to have a tractable problem here. We would like to find simpler functions Q that approximate P, and then we can use these Q functions instead of the complicated P functions. Now this is what we had from last lesson. This was the way we expressed this for the expectation maximization algorithm. Here we had this expression here that we used the this is our posterior here, right? The log posterior actually, P of x, and we split this up into a lower bound and something which is called the Kl divergence, right? We said that we can now express this P as a sum over this thing here, L of Q and Kl of Q, where Q is just some other distribution, right? Just some, and this holds for any kind of distribution of Q, right? And the trick was now to have this iterative approach in EM, where we first find a Q that maximizes lower bound, and the lower bound was maximized by minimizing the Kl divergence. And then once we have that, we re-estimate a new parameter set, right? And then find another approximation to this P, and then this goes iterates. Now we simply say, okay, we take this general approach again. We say we subdivide our problem again into some lower bound plus some Kl divergence. The lower bound is defined like this here, right? Here again we have our joint probability here, which we actually estimate. In DM we call this the complete data likelihood or log likelihood, right? Where we have the x, which is the data which is observed, and z is unobserved. And this was easier to compute than the actual posterior itself. So we used that here in this framework, and we used the so-called Kl divergence, which is this thing here, and this is defined by the negative integral of this here. So again, maximizing the lower bound here is equivalent to minimizing Kl divergence, and this is what we will do here in variational inference as well. Also, what we said already last time was that the maximum is then reached when the Kl divergence vanishes, which is 0, and this is the case where Q of z equals just our posterior here, P of zx, a given x, right? If this is true here, if we find the correct posterior, then the Kl divergence is 0, and then we can be certain that we have the lower bound maximized. However, and this is now the trick here, or the whole idea of variational inference, this can't be used very often, right? In many cases, this posterior is intractable to compute, and we cannot simply say we take the Q equal to the P, right? But however, what we can do sometimes is we can find a simpler Q, which we now know how it looks like, but we know that this Q is very close to this P, and then we can then use that to make it tractable. Okay, some more words about the Kl divergence. Kl divergence is probably the key notion in this whole thing of variational inference and all this topic here. I said this already, I think, last time. This is another way of interpreting the Kl divergence. If we have an unknown distribution P, then we can approximate that with a known distribution Q. This is the idea. And then the Kl divergence is the so-called, can be interpreted as the average additional information that we get by using Q instead of using P. And how can we think of this? What does this mean? Well, if you split this up here, right? So the Kl divergence, if this is the definition of the Kl divergence here, we can write it also in this way, right? This is like a slightly different way of writing the Kl divergence. And what we see here is that this thing here is kind of the entropy where we just replaced P by Q, right? This is just what Q tells me about P, or what's the difference in representing one distribution with the other. And of course, we have some kind of more information. Like the intuition behind this is we need more information, right? More in the sense of entropy, to represent P with Q, and the amount of more information is just the difference of that entropy with the true entropy of P that we actually do, right? This is the entropy of P, right? This is just the amount of information that P contains itself, and this is what we have additional. So that if we subtract one from the other, then this is the additional amount of information that we need, right, to represent P with Q. Hope this is kind of clear. This minus sign, if you just, I hope this is clear that this is the same here, right? So this can be then written into one integral, right? Or we then have two sums. This is we have a sum in the integral. This is P of x times, and we can then write this as parenthesis log of Q plus a minus log of P, right? And log Q minus log Q can be written as this factor here, as this fraction here, right? Is there any question on that? Is that unclear why this is? Okay, so this is, we say this is the Kl divergence, and it has some very important properties. First of all, it's not symmetric, so it's not a real metric, right? We cannot say Kl divergence is a metric because the distance, if you interpret it as a distance between two distributions, then the distance between Q and P is not the same as the distance between P and Q, which is not really nice, right? It's not. We cannot really nicely use that as a metric. But it doesn't really matter, right? It turns out that you don't really need to have such a metric, right? So, but we have to be aware of that. So if we now try or find algorithms that minimize the Kl divergence, we have to say which kind of Kl divergence we actually minimize, this one or this one, right? Because they are completely different algorithms. The outcome is completely different. Another important property is the Kl divergence is always positive, right? And if it's 0, then only then we know that P equals Q, right? And I think we had this already last time. I skipped the proof here. It's all in the book. If you want to have the proof, then you can do this on your own and try it out. It all follows from this Jensen's inequality. I don't think it's necessary to do this here. I mean, this is just for you to know that these are the main properties of the Kl divergence. Okay, now the whole trick now, and one important idea of variational inference is to use to simplify Q, or to restrict the Q distribution, which is the one that we use to approximate P, by a factorization. So one idea is to assume that Q can be partitioned, can be factorized into a set of factors here. So what we do here is, and I think this is important to understand here, we have Z, which is a set of variables, right? Random variables that we have in our problem. And we assume that we can subdivide or partition this set into disjoint sets, Zi for 1 to m, right? We have m subsets of our big variables. So we have a number of random variables. And we have subsets of these random variables. And now the idea is, or the assumption is, that our Q function that we try to find can be factorized into this way, right? So we have m factors, and for every factor we have a distribution, and this distribution only works on the subset of variables, right? Zi is just a part of Z, and every Qi only is a distribution over this part of Zs. This is the only assumption that we have about Q, right? But this helps us a lot, because then later we can see that we can now go factor by factor to find an optimal Q that minimizes the Kl divergence between Q and P, right? This is the whole trick, right? We want to find a Q that is close to P in the sense of the Kl divergence. Okay, now the idea is to optimize this lower bound, again, with respect to each factor of Q in turn, right? So we have these factors here, and now the trick is to pick one factor in every, so we have an iteration, and in every iteration we pick a factor, and we optimize that factor so that the whole factorization gets closer to P, right? So we have this big, long thing, Q1 times until Qm, and we just pick one and optimize it a little bit so that the whole factorization, the whole Q thing gets closer to P, right? Yeah, so, and I'd like to show this a little bit in math, how this looks like. So we have, what we can now do is, now we can have, I'm writing this down here. It's also explained in the book here. On the whole chapter I'm talking about here is chapter 10 in Bishop's book. And I'll try to kind of explain the idea of this formulation here. Not going to through the whole math in detail, but I think it kind of gives you the idea what this factorization, how this works here in this case. So we have the lower bound, L of Q, which is defined by, we had this already, by the integral over Q of Z, yeah, times log Q of Z, P of Z divided by Q, P of X and Z divided by Q of Z, dz, right? So this is the functional that we look at, right? Again, we have an integral over all hidden variables. Z are the hidden variables, so we integrate them out, and X is the data that we actually observe, right? This is the set of variables that we actually observe here. And now what we simply do is we plug in our factorization of Q into that lower bound function, right? So the Q of Z and Q of Z appears in these two parts here, and we just plug in our factorization, which is simply now the product over all factors Qi of Zi log, and we have now the same P of X and Z divided by factorization Qi Zi dz. First of all, what we also have to note here, this dz here, again, z is a set of variables, right? It's not one variable. So if we do an integration here, what we actually do is we do many, many integrations, right? In fact, we have like many, many integrals here, and for every integral we have a factor here, right? We could also write it like this here. We have like many, many integrals, and we do this here, like that. We have all these subfactors here. Right, and this is the whole trick about this. So now we can, first of all, we can write it like this here, right? Now the thing is, we split up the log, right? This comes out. I still write it now with one integral, but we keep in mind that we have many integrals here, right? So this is now the same as Qi times, and this is what we just written there on the slide, which is log of P of X and Z. Minus, and now we can now put, this is of course minus log of that, and we can now put the product in front of the log, and this turns it into a sum, right? We have now this here, log of Qi times dz, right? Is everyone clear that this is the same as this, right? Is any questions on that? All right. This, the only thing is just putting the product in front of the log, and then it turns into a sum. This is just the rule of product and sums with logs, right? So now, the next step is still an easy one. We now split this up into two sums. We have now two integrals. The first one is this one here, Qi log P of X and Z, minus the integral, and now we have again the product I Qi sum I equals I1 to 1 log Qi. And of course I need dzi and dzi here. Also, what I'm setting here is we have a simplification here. So Qi is actually a distribution, right? We write it now just with Qi. We should write Qi of Zi, right? We don't do this because it's just a lot of writing, but in general we have to think this is not a value, it's not a real value, this is a distribution, right? And we integrate over all values of that distribution, right? This is still a little bit probably hard to understand that this actually works, right? Right, so if I write now dz, again I can write dz1 to dzn, right? So this is all the variables, all the subset of variables are integrated here. And now comes the very much like the trick of of this factorized idea of this, it's called mean field technique. The trick now is to pick one particular factor out of this big factorization out and only look at this one, only optimize this lower bound here with respect to this one factor, right? So we have to write this down as one factor, and we can do this by now looking at one particular factor qj, right? And then I first write it down and then explain what means here. So I pull out qj, and inside all the other factors remain p of x and z times the product over all i's that are not equal to j, qi, dzi, right? So this is just the first term here, written in a slightly different way. Why is this the same? So first of all, inside of this here, again, we have many integrals, right? These are just many integrals because these are the integrals over all factors which are not equal to j. This is just all the rest. And this is just this one particular factor pulled out of the sum of this integral, right? It just, if I pull it in again, then I would have the product here with all i's, including j, right? And then I would have the same as here. Questions? That's unclear? Yes? Well, the trick here is to now be able to just look at this one factor, minimize this with respect to that factor, and optimize L so that, so find a new qj so that this is closer to p, so that the lower bound is optimized only with respect to qj. And then I do this iteratively. I go in a big for loop, I go over all factors and do this for every factor independently, right? I take the first one, the second one, the third one, and instead of doing this at once in one step, I do this stepwise for every factor independently, right? This is the trick of the mean field algorithm. Okay, and the second part here is a bit more. It also works, right? It also works that we can now pull out one factor, but it's probably not so directly easy to understand why this is the case. I just write it down first how it looks like. Here we have qj log qj dzj plus some constant. So how can we see this? For myself, I try to understand this with a simple example. What we have here is we have a product over terms times a sum of log of these terms. So this is a product times a sum. And in the end, we do an integration over all these. So in the end, what we could look at this, let's say we write these terms qi as a, b, and c, right? It's just 3 terms. Probably it's a bit confusing, but I try to understand that this is actually the same. So we could have something like we have a times b times c integral time over a plus b plus c, right? These ABCs are nothing else than these QIs here now, right? Sorry for the kind of new thing, but this is just to give you an intuition that this actually works, right? And then we integrate over these dA and dB and dC, right? So we have actually 3 integrals here. This is what happens here when m equals 3. So this is m, number of factors, right? And this is m, and this is m, right? This is the number of factors. So what happens here is we have a product, and we can now write this as ABC times A, log A, sorry, this is important. This is log A, log B, and log C. So log A plus ABC log B plus ABC log C. All right? Now again, the trick is to write this as 3 different integrals, right? And then what we have is, in the first case, we will have an integral ABC log A, dA, right? Which that means that, dA, dB, dC, of course, we integrate 3 times. Now we can pull out BC, and it comes out that this is A log A dA. Why is that? Because B and C are distributions, and if I sum them up, then they're 1. Right? What remains is just A times log A. Right? I hope I don't confuse you too much with that. This is just the way how this happens, right? This Qj here, the one particular factor that I take out, is in this case our A, right? All the rest integrates to 1. Right? Because it's distributions, right? This BC can be pulled out, and then we have inside we have a factor which is this one, and outside we have something simply integration over things, because it doesn't appear as a log in here anymore, right? The B and the C don't appear as a log here, which then means if I integrate over them, they are 1. And the same for these other two, but these other two, these are independent of A. So if I only look at Qj, then the whole thing can be considered as be constant, right? I only want to have this part here, which is just the only term here that depends on Qj, right? Yeah, that's it. I think this is the this is all we need, and this is just another way of writing that, right? So this thing here, now this is an important thing here. To write this simpler, there's a nice trick. This can be looked at as an expectation over some distribution, right? This is also a very common trick in statistical analysis and stuff. So here we have an expectation over some value for a given distribution. So the value which we have here is this log of P of X and Z, right? This is the value, and this is the distribution. This is the probability of that value, right? So expectation is nothing else than an integral over all values of a given distribution times the probability of that value under this distribution. So here we have a distribution which is again a factorization, but it's missing one factor. But it's still a distribution, right? We still have a valid distribution here because we assume that we can subdivide our Q function into factors. We're missing one factor, but doesn't matter, right? We just have another kind of distribution. So what we write is here we have now a distribution over all factors apart from J, right? So it's an expectation under this distribution. And what do we take the expectation on? Well, this is the value that we talk about. This is the log joint, right? The joint of the log of the joint probability, right? So this is the way we write this, and we call this P tilde, log of P tilde, which is simply again our this is our distribution here, and we can also just pull this constant term inside here. So what we then have is, right, that our lower bound is nothing else than the Kl divergence of, this is another insight here. This lower bound here again can be interpreted as a Kl divergence, because now we can pull these two things together again, right? Now we have a distribution here. This is one kind of distribution, and another. And this is the entropy, right? We have Q and Q here. This is the classical definition of entropy, and now this is simply the Kl divergence between our actual factorization and our P tilde here, which is this expectation over all factors which are not J, right? Right. I hope this is clear again, right? We can now write this whole lower bound thing in terms of this. It's basically another Kl divergence with some constant thing in the end, right? So that means again that if we minimize this LQ, then we have to maximize. To maximize the lower bound, we have to minimize the Kl divergence, right? Because there's a minus sign in front. That means again we have the same thing. If we want to have the Q that maximizes lower bound, we take for this particular factor J, we take the one that minimizes this Kl divergence, right? And we do this for all factors J in turn, right? We have a big loop over all J's, and in every step we take the factor that minimizes this thing here, right? and does it in terms of this expected log joint probability, where the expectation is taken under a distribution that takes into account all factors but the one we're looking at. Right? So this is a general description of the mean field theory and the technique that can be developed by this. So to generalize this in words, or to write this down here, the optimal factor in every step j, the optimal factor qj, is the one that comes out of the expectation over the log joint, where the expectation is taken over the probability, where we take all factors but the jth factor plus some constant factor. This constant thing here, this is all in log space. So if you take the expectation over that, then this would be a product over some constant thing. This constant thing is nothing else than the normalizer of our distribution, right? This thing is something that just guarantees that qj is again a distribution. That means we can find ways to compute this constant factor by simply normalizing our distribution here, right? If we have ways to do that. But very often we don't have to do this, right? This is important. The constant term does not have to be looked at very often, or we don't always need to do this normalization thing. Important is just to have a way of writing this joint posterior here and taking the expectation over that without looking at the factor j. Okay, this is the general way. Later we will apply this general technique to a concrete problem. And we'll see, I think, in more detail how this works and why this works. Before we do that, we have to do some kind of excursus. We have to step back a bit and explain some things about conjugacy and what are conjugate values of conjugate distributions. So yeah, so let's first of all keep this all stuff in mind and start kind of again from some complete, first of all, different kind of way to look at the problem. We'll later see that this whole thing comes together. Assume we have a binary random variable, a very simple random variable, so x, right? X can be either 0 or 1. And we're given a parameter mu, and this parameter mu is between 0 and 1, right? With this parameter mu, we can then specify our distribution. We can say, if I know this parameter mu, then I can compute the probability that x is 1, which is exactly the same as mu, right? This is a very simple coin flip example, right? We have a coin and we assume that we know this mu thing, right? Mu can tell us how biased the coin is, how probably is it that we have one step or the other. So that means the probability of being head is mu, and the probability of being tail is 1 minus mu. Together, if we put this together into one distribution, we can write it like this here, which is kind of a more complicated way of writing it, but it gives the same result. So p of x given mu is something like mu to the x times 1 minus mu to the 1 minus x. This is called the so-called Bernoulli distribution, which is a very simple distribution over binary variables. Now assume we have a set of data, right? We have observations. It's not only one observation, we have n observations, and we assume that they're independent. Then we can compute the probability of this whole observation, of these n observations, by this here. We say the probability of the whole data set, of the whole n data points, given some parameter mu, is just a product over all these data points. And we can write it now, again, we plug this in here, we plug our Bernoulli distribution in here, which is simply that the product over all these Bernoulli distributions. We can also write it like this. We can say, we can split this product up and say, this is the product over all cases where xn equals 1, and times the cases where xn equals 0, right? This is the first thing, and the second thing, we just copied that. Now we plug in xn here and 0 here, which will then end up with something like this here. So here we have a problem, the probability of d given mu equals mu to the m times 1 minus mu to the m, where m is just the number of events where xn equals 1, right? This is just the definition of this. Yes, and now the next step is to find, so if we want now to have, in general, the probability that we have m positive events, right? We then have simply to multiply our data, or this distribution here, with the number of possibilities that we can have m events in n cases, right? So n n choose m is the binomial coefficient here, which is simply the factor that we need to put in front of this to get this distribution. This is called the binomial distribution. Now, why do we do all this? So assume we'd like to find this parameter mu, right? So we would like to have a way to estimate mu from data, right? So assume we have some data points xn to x1, and now we'd like to find mu from this data. This is again the formulation from before. I don't write the binomial coefficient here now because we actually don't need it later in the optimization thing. We could think it here, but now we anyhow derive with respect to mu, and then the constant factor will cancel out. So to do this here, I can do a very simple computation here. I think this is the computation we did already a number of times. And it's the standard way of doing it. It's just taking that expression there and deriving it with respect to mu and setting it to 0, right? So we have the sum. This doesn't write. Where's the other one? Of all data points of xn log mu plus 1 minus xn log 1 minus mu. And now what we do is we derive that. First of all, I think we write it slightly different. We say mu is independent of n, so we can write this like log mu of times a sum over n xn plus log 1 minus mu times n 1 minus xn, right? So this is just taking into account that this part can be pulled in front of the sum, right? And we split this up into two sums, right? Now I derive this with respect to what's it called, the term? So we derive this with respect to mu. This is P of D given mu with respect to mu, which is the same as, now we just take this here, this is 1 over mu, times, this stays the same because it's completely independent, plus we have 1 over 1 minus mu, and the inner derivative of this thing is minus 1, so we switch this to minus, and this thing stays also the same. Right, and we set this to 0. This is just a standard way of doing this. Machine learning is a lot of basically just nothing else than optimization. We just derive this with respect to our parameter that we'd like to find, set it to 0, and find the mu that minimizes that. So to do that, what we can do is just say this is the same as 1 over mu sum xn equals 1 over 1 minus mu sum over 1 minus xn. And now we do the standard trick. We multiply with 1 minus mu on one side, and we divide by the sum equals sum 1 minus xn divided sum xn. This is the same as 1 over mu minus 1. And this is the same as sum over 1 is n over sum xn minus 1. Right? Questions on that? Because this is the sum over xn cancels out. Right? Okay, now the 1 cancels out, and now we just turn it around and say mu equals sum over xn divided by n. And sum of xn, we have already a way of describe that is nothing else than m over n, because this is the number of positive events we have, right? So this is our result. We obtain that mu, the optimal mu that fits into that data is the one that we simply take we just count how often we have had and divide it by all cases that we have. This is just taking averages, right? Nothing else. It explains again that this is maximum likelihood, right? we only look at the data. To optimize the parameter in MLE, what we only do is take the optimal parameter so that it fits best to the data. But that's a problem. That's a very big problem, and we had this already. Maximum likelihood estimation has the big problem that it can overfit a lot. And one very simple example on that is, suppose we have only ones. We have observed 3 ones, three times head, 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 which is possible, right? We have just a very small data set, and we have a coin flip, and the coin just flips, like, for some reason we have 3 times the same thing. In that case, if we would like to find now the optimal mu of that, we would have that the probability of being ahead is exactly 1, right? Because m is 3 and n is 3. That means 3 by 3 is 1. That means the probability, this our parameter here, our bias of the coin is just 1. Which would mean that this model, this maximum likelihood estimation, would predict that we always see head, only because of the fact that we saw 3 times head. Which doesn't make sense at all, because we know that coins sometimes have tail, right? Even if we find 3 times one result of the experiment, we know that coins in general, at some point, they must have the other one. Even if they are very biased, at some point, there must be the other one. And this is the reason why we use, instead of maximum likelihood estimation, very often we use the posterior. So we compute the posterior, and the posterior is, again, nothing else than applying Bayes' rule. And this is the reason why it's called Bayesian Inference. Bayes' rule simply says we take our likelihood, which is what we computed right now. We have some kind of prior information about what happens here. And prior just means we have no data given, right? There's nothing we know about the data, but we have some kind of intuition, some idea of this model. So we assume some kind of probability here. And if we multiply the prior with the likelihood, and we normalize it, of course, then we obtain another probability distribution, which is then called the posterior, right? The posterior is nothing else than the distribution over our parameters here. These are the unknown parameters given our data, right? And yeah, this is just nothing else than, I think, the very first lesson, just applying Bayes' rule to that, right? And now the trick here, or what I'm going to looking at, is to find nice priors so that the posterior is still in a nice form. So in variational inference, I said this already, we're talking about distributions and functions, and we would like to be in the same space of functions, right? We don't reason on points, we reason on distributions. So that means if I have a functional description of my likelihood, for example, a binomial distribution or a Bernoulli distribution, then I would like to find another very nice proper way to write the prior so that the posterior is in the same functional form. Because then I can do an iterative approach. I can then use the posterior again for the next prior in the next round. This is the main idea of that. So I want to have a description so that this functional form stays the same. And it turns out that for many, or from the most given distributions that we know, for example, Bernoulli and binomial distributions, there are priors that go together well with that distribution. So if I use that prior and multiply it and normalize it, then I have the same kind of prior in the end, right? And these kind of priors are called conjugate to the likelihood. So if I have a given likelihood distribution, I can use a prior so that the posterior is in the same functional form. So for the particular case of the binomial distribution, our observation is that if the prior is proportional to the powers of mu and 1 minus mu, then the posterior will be so too, right? This is the whole trick about it. And just to show this intuitively, I'm not showing too much detail here, but I'm just showing here how this looks like. We had the likelihood of so let's say the binomial distribution. The binomial distribution was this n over m times mu to the m times 1 minus mu n minus m, right? This was the binomial distribution that we had. And now we would like to find another distribution so that we multiply that with this, we keep the same functional form, and we observe that it should be something that is proportional to these kind of terms of the power. So if we take, for example, a distribution that is some kind of x thing that we don't know times mu to the a times 1 minus mu to the b, right? If we have this kind of functional form, we multiply this together, then we kind of understand already that in the end we'll have something similar to what we have already. We have some kind of factor in front, which would be something like this here, but then we have again mu times m plus a times 1 minus mu to the n minus m plus a plus b. So we have a kind of same functional form. And this turns out, if we go further into that, then we'll find out that the beta distribution, which is defined by this thing here, is exactly what we want, right? This is exactly the conjugate distribution for the binomial distribution. So if we know that our data, or if we assume that our data is binomial distributed, to find a good posterior, or to find do maximum posterior approximation, we should use a beta distribution, right? Beta distribution is, I'm not going into detail. This is just the gamma function here. Also, it has two parameters, the beta distribution A and B. These parameters they don't have to be integer numbers. They can be real numbers, but they must be positive. And the idea and the trick is, if we apply this now, right? If we now plug this in here, then the outcome, the posterior we compute from this, is again a beta distribution, right? Now with some different parameters here. If on the prior beta distribution starts with a minus 1 and b minus 1, then the posterior has m plus a minus 1 and l plus b minus 1, where l is just the difference between n minus m, right? The nice thing about this is we can now interpret this here, because now we can say, here we have a beta distribution with m plus a and l plus b as parameters instead of a and b. And that simply says that we can interpret a and b as the number of positive and the number of negative events before seeing any data. That is how much we think before seeing data, how much is this distributed, how many tail and how many heads do we have before seeing the data, right? Okay, and this is just an example before we go into the break. This is one example where we assume this is the prior here. So again, we don't have data here. We assume that our coin is kind of a fair coin, and we say the number of cases for tail and the number of cases for head is the same. In this case, it's 2. A equals 2, B equals 2, and then we have this kind of prior distribution of our value here mu. So it's symmetric, and the most likely value is in the middle. So we can't say which will be the next, which will be more likely to come next in the first observation. Then we have this likelihood function here. This is just a line. This is just the identity here, because we only consider one data point, right? We sample one sample. N is equal to 1, and we assume that this one sample gives us head, which is 1, right? So we get, as a result, we get 1, right? And we can now plot the likelihood function in terms of mu, right? For every kind of mu that we assume, we find a different value here, and this is just the function between, this is just the identity here, right? 0 and 1, right? We have to make sure, know that this is not a distribution, right? It's a function. Distribution is not a distribution because it doesn't sum to 1. Sorry, but it doesn't. So it's not important here. For now, we plot this in terms of mu and not in terms of m, right? So that's the reason why this is not a distribution. But then, if we multiply this together and normalize it, then posterior it looks like this here, which makes complete sense, because now we have a distribution that is slightly biased towards 1, towards the A thing. A is just 1 more, and B stays the same, because we have observed 1 more head. And now the probability that our coin gives us head is more likely than it gives us tail, right? And we have only the difference from this to maximum likelihood estimation is here we only observed 1 data point, but we still are not too much biased to this one thing, right? We still keep in mind that there might be possibilities that we have tails from the coin. This is the important part, and we do this with all this with closed form. representations by using this conjugate priors. I think I should do some more on that, which I'm not showing in too much detail. We can also explain that in more with other distributions. For example, for the multinomial distributions, where we have not only 2 outcomes but many outcomes. We have a dice, right, with 6 outcomes, for example. Then k is 6. We have 6 states here. For every state, we have a probability. The sum over all these should be 1, of course, and they're all bigger than 0 or can be 0. So this is the definition of the multinomial distribution. It's all slightly different here. We have now a subset of data points, k data points, and this is the multinomial coefficient. Again, I'm not saying too much about this, but it's not much different. It's a bit more, let's say, more math, but it's basically the same as binomial. And if we take the multinomial distribution as the likelihood, then we need the so-called Dirichlet distribution as the prior, which is then the conjugate prior to that likelihood, right? This is something about the Dirichlet distribution. It's defined by this, again, with gamma functions. A0 is defined as the sum of all other k's, and the mu k's have to be between 0 and 1, and they have to sum up to 1. One example to visualize Dirichlet distribution is always a triangle here. So it's a simplex in 3D. We have 3 variables here, and because they have to sum up to 1, because they are between 0 and 1, all these mu's here are distributed in this triangle here. It's a simplex of order 3. Okay, now we have a break if there's no questions. Okay, let's go on. So in the first hour we had we were talking about a general way of describing variational methods and what can we do in general to factorize, or how we can use factorization of distributions. And here we would like to have a concrete example that shows you a little bit how this can look like in practice, right? This is again an example that's taken from the book, so all the details that I don't show here, you can then look up in the book. It's nicely written there and explained, and I'm trying to get the idea about this, right? Not go, let's say, not explain every little step, but try to get the idea what's happening here. And why is this different from what we had before? We were talking about mixture of Gaussians already, particularly when we talk about EM, right? EM is a method to estimate parameters for a mixture of Gaussians. Again, we start with some data. We have some data X. We have some latent variable Z. And now, furthermore, instead, we not only have this here, we have also some parameters. So in general, I think what we can say, we can write this down in a graphical model in this way here. We have observations here, xn. We have latent variables here, zn. And according to these latent variables, we have some parameters p here, pi, lambda, and mu. And so the zn's are the mixture, or the binary variables that say the correspondence between data points and Gaussians. And these are parameterized with some pi here. And pi is, now that we know that this is a multinomial distribution, right? We have this already. Multinomial distributions give us the probability that a data point corresponds to a Gaussian, right? This is how we describe this. That means every data point has k possibilities to be assigned to, and this is the concrete case of a multinomial distribution, right? So every one of these data points n from 1 to n has a probability, a given probability, to correspond to one of these Gaussians, of k Gaussians, and the parameter that we use for that is z. Z is a binary variable that says yes, data point n corresponds to Gaussian number k, and if this is the case, then this is 1, otherwise this is 0, right? This is just the way we write this here, the multinomial distribution. And yeah, this is one thing, and the other thing is our Gaussian itself, right? Now we have parameters for the Gaussians, which are mu, and in this case, it's the precision matrix, which is the inverse of the covariance matrix. It's nothing else than that. It's just another way of writing it. And we have again our Z values, which are now observed, which are now given, let's say. We have this on the right side. We say, if we know the correspondences from data points to Gaussians, then we can compute the probability of a data point, right, under this distribution, because it's just the product over all these Gaussians here. And now the trick is now to write this not only as a likelihood, but also add some priors to it. And for every parameter that we have in the model, we find a prior that is conjugate to the likelihood it corresponds to, right? This is the whole trick about it. So if we have a multinomial distribution over the latent variables here, which are the correspondence variables, then to find an appropriate prior for that, we just need the one that is conjugate to the multinomial, right? This is a multinomial. The conjugate to the multinomial is a Dirichlet. We said this already. So we have to find that p of pi must be a Dirichlet, so that when multiplying this with this, I still get the Dirichlet, right? I still get, I'm in the same space of functions or distributions. The same is true for the case where I have a Gaussian where I don't know mu and covariance matrix, right? Here, what we can find out is, I mean, I'm just giving this as an information. I didn't explain this. The conjugate distribution for the Gaussian, where in the case where mu and lambda are known, is the so-called normal Wishart distribution. And the normal Wishart distribution is defined like this. It's a product of a normal and the Wishart distribution. I'm not going into details of that. It's a bit more math, right? But you can prove that this is the conjugate prior for this one here, right? This is just what you need to know. Now, what you then have is we have a one big joint distribution, right? The probability of all the parameters, all the data, all the hidden latent variables, everything that we have is one big joint distribution. One note, when I'm talking about parameters and I'm talking about latent variables, there's only a slight difference here, and this is also noted in the book. So Zn are the latent variables, and parameters are outside this plate here, yeah, which is kind of the only distinction that we have here, right? Other than that, they're completely the same. It's just another random variable, where the only difference is that the latent variables, they occur as often as we have the data. For every data point, we have a latent variable, but like diagrammatically or mathematically, these are basically exactly the same things as parameters, because we now consider parameters again also as random variables. And this is the whole trick of the full Bayesian approach, right? Full Bayesian approach means that every parameter in the model itself is a random variable, right? Of course, this gives you other new parameters, right? Because the prior to all of these parameters itself, they have parameters, right? But these are called hyperparameters because they kind of only influence the parameters, right? So it's another step of parameters, right? Okay. Just as a note, let's look at this again. We have this joint distribution over all these parameters and variables here. We can write it again. This is our Gaussian. This is the probability of our latent variable here, right? And now we have the prior for that one, right? The prior for this one, and so these two things together are the prior for the Gaussian, right? And now we would like to apply our mean field theory, mean field factorization to this problem here, right? So we like to find, for the moment we think that this is a very complicated thing to do, right? We cannot easily do this. So instead, we would like to find distribution Q, which is another factorization, right? But we want to find the Q that is very close to that P. We want to approximate P with some Q. And to do that, we use our general results. We say if we take a factor out of that thing, then what we'd have to do is we have to take the expectation over all other variables. If you just take, like in this case, we take one variable out, which is z, right? This is one part of this whole big set of variables that we have, just one subset, which is this z in this case. which is nothing else than expectation over the log joint, right, of the whole joint, where we take the expectation of over the distribution, which is a factorization again over all other variables. It sounds complicated. I think it's the same as we had before, right? The expectation we have here, right, is expectation over some under some distribution, and this distribution is a factorization over all factors that don't include our z here. It's p, and of course not the data. So it's just p, mu, and lambda, and z is not in there, right? But z is in here, and the data is in here. So we have some kind of way to express this thing here, right? But to find a good Q, we can now like compute this here. We assume that this is tractable, right? To compute this expectation here is easier, or is tractable. Now what we can do is we can now plug this in. So we now have our factorization here, right? This is something we assume we have, right? So we can now plug this in. So the log, if we have this is a product here, the product goes into here, then this turns into sums again. So we have expectations over these. So we have a sum of expectations plus some constant term, and if we do this over and over again, and we do more computations on that, then it turns out that the optimal factor Q is something which is very similar to a multinomial, right? I'm again not showing the details. In the book, there's all the math and all the derivations of that. If I did this here now, it would take me an hour. I think it doesn't make sense to explain this here too much because it's kind of leading too far, I think. For you just to know is the optimal, if I use this mean field theory and I take one factor out of this big factorization here, in this case, I assume that Q is a factorization of some hidden variables times a factor of the rest, right? The optimal factor here is exactly what we already have in our model, right? Which makes sense because this is then the closest Q to P, right? Right? I mean, now we know that this is a multinomial, right? But in case we don't know, we can use that technique to find something which is very close to the truth. Is that clear somehow? Okay, this means that the optimal solution to the factor Q has the same functional form as the prior of Z, right? So the prior that we actually, this prior here, no, this is, it should be the likelihood, not the prior, is a multinomial, right? It's the multinomial, and the prior of it is Dirichlet, but so this should be likelihood. It turns out that this is true for all factors. We can use another factor, and this is the same thing, not only for this particular factor. The only problem that we have to look at, what I didn't show here is that this, to compute this factorization, it depends on all the other terms, right? So it's not a one-step thing to do, right? In computing that, I assumed I knew the other factors, and I don't know them, right? So the trick is I have to start with this is an iterative approach. I have to first initialize all the other factors here, then compute Q of Z, and then do this for the others as well, right? This is like a slightly different thing. So instead of just using this in one run, I have to do this iteratively. But the whole idea is like that, right? The variational inference algorithm just works like this, that I pick out one factor, optimize this so that the whole factorization is closer to P in terms of the Kl divergence, and then I take another one and another one, another one until I reach some convergence, right? This is not a one-step thing to do, right? In the end, we have something like an EM style algorithm, with the difference that now we use conjugate priors for all the parameters, right? Now we have a full Bayesian approach. Full Bayesian means that every parameter in the model has its own prior. So we put a prior on every parameter. That means we kind of introduce some prior knowledge into the system, prior knowledge which is independent of data. And by doing that, we reduce overfitting. This is the whole idea of it. So when we did EM, we only had a maximum likelihood estimation, right? We only looked at the data. But now we have expression. This is the similar experiment that was done before already. We have these two classes here, and when we did this with EM, we needed to know the number of classes, otherwise EM wouldn't work. Here, as we introduce some other knowledge in terms of the prior, we can now start with a higher number of actual clusters here, if you do clustering on this data set. And it turns out that after some kind of number of iterations, we will end up with 2 clusters, right? The trick here is that some of the clusters that just go to 0, that the weights of these clusters, they go to 0 or go very, very small, and then we can remove them, right? And this is a nice way of showing that with MAP, maximum a posterior estimation, we can reduce the risk of overfitting, right, into one data set, into one data point, which we had in the EM, right? This could happen in EM that a Gaussian would just fit to one single data point, and this is not possible so much, or doesn't happen so much with if you take the prior into account and if you estimate the posterior of that. Yeah. One note, of course, this again, no algorithm is without parameters, and of course, this algorithm here, instead of parameters, it has hyperparameters. And one of the hyperparameters is this parameter of the Dirichlet distribution, right? The Dirichlet distribution itself has a parameter, and if we change that parameter, then we have also different behavior here, right? If we have, this is also explained in the book, so it can then even happen that we have like 3 or more classes in the end, right? Which is incorrect, but this is, let's say, easier to define, because then this can be tuned easier, right? Than if we don't have a prior, right? Well, first one thing is they converge much slower, and then in general much slower, right? Because you have more computations to do. Okay. Yeah. So this was one part, one algorithm. And another one, which is a very important one, is so-called expectation propagation. The expectation propagation takes very similar ideas from variational Bayes, as we called it before. So variational Bayes means we take a variational approach to do a fully Bayesian formulation. This one is very similar in ideas, but it does a completely different thing, and it comes and it works in different kind of cases, but it works quite well in these other cases. First of all, as I said already before, we have this Kl divergence here. This Kl divergence is our measure that we want to optimize. We want to find a Q that minimizes this Kl divergence. So in mean field, in variational Bayes, what we did is we optimized this Kl divergence, Q and P. What we also can do is we can also minimize the opposite. We can minimize KL of P and Q, which is just turn this around. And this is what expectation propagation actually does. So, and another, let's say, assumption that we have in AP is that Q can be expressed as an exponential family. Exponential family is just a very general description of a class of distributions. For example, a Gaussian is one part of this. You can imagine that a Gaussian can be expressed in terms of H and G, so that we can find, so we can set H and G and eta and U, so that this is a Gaussian, but other distributions are also members of this exponential family. This is just a way of having a more, let's say, general way of describing it, and we need that for the description of the EP algorithm. So before we had Q, the only assumption about Q was that we can factorize it, right? So we don't have this restriction on exponential families, but here we kind of assume that Q is a member of the exponential family, which is not a strong assumption, right? Many distributions are members of that family. So important also to know that the normalizer here, G, right? This is simply, so G of eta, if you just divide by this whole thing, is 1 over the rest, right? This is just to make sure that this is a distribution. G is just a normalizer, which is just 1 over h times exponential eta times u of z, right? Okay, now we have this different Kl divergence, which is P given Q. And to do that, we can simply plug this in, right? And write KL of P and Q. I think for completeness, I just write the definition of KL again. KL of P and Q is minus P of Z log Q of Z and X divided, given X divided by P of Z dz. Right? And now we just plug in Q here, right? This is our exponential family, and we come up with this, right? We know, of course, there's a dz missing in sorry for that, equals P of Z log, this is the exponential family, H of Z H of Z Q of eta, no, G of eta, sorry, exponential eta times u of x divided by P of Z dz. Now the first thing we do is we write this as a function of eta. Eta is the parameter that we want to find, right? Would like to find, this is the kind of the parameter that specifies our Q function or Q distribution from the exponential family. So we would like to find an eta that is, so that Q is very close to P, right? So as a function of Q of eta, this can be written as P of Z log eta H of Z. Let's say, okay, I write this whole thing first like this, plus log of G of eta plus eta transpose times U of X, U of Z, sorry, U of Z, minus log P of Z dz, right? This simply writes the log of the fraction again as the sum of logs, right? This is just again turning this around. And now we look at only the terms where eta appears. This is this term here and this term here. And all the rest, we say it's constant, right? So we can say that this is, first of all, this is minus P of Z times log G of eta dz minus P of Z eta transpose U of X dz plus constant. Constant in terms of eta. Right? Now this is again a nice trick here. Now we can pull this G of eta out again because it's independent of Z. Right? This is the same as minus log of G of eta. And inside remains just the integral over P of Z, which is 1. Right? We just skip 1. Minus, and the same here, eta can be pulled out here. Right? We have now eta transpose. And inside remains something like P of Z times U of X. And then the integral of that, which is the same as the expectation over U of X under P. I think this notation appeared already a number of times, and the more often it appears, the clearer it gets, I think. The more you use that, the better you understand what this is, right? This is simply an expectation under a distribution of some value, and this value is just U, and we have the distribution P. So under the distribution P, we have this expectation, and we have some constant here, right? And eta is in the front. I think this is the next slide, what it says. Yeah, exactly. So now Now this is again our Kl divergence, and what do we do now to minimize that? Well, again, we derive it with respect to the parameter that we want to have and set it to 0, right? This is all we do. So now this is a vector, can be a vector, that means the derivative of the vector is the gradient. So we take the gradient of the negative log of g of eta, and this should be equal to of course, we have to derive this with respect to eta, which simply is the factor in front of the eta, right? Eta just goes away because we derive this with respect to eta. This is exactly the same as E under P of U of x. Plus some constant, which also goes away, right? So this is the next slide, I think, right? So to find a good Kl divergence, we need to find the term d of eta, so that this is the case. Now there comes a little observation from the general description of exponential families. So this is a very nice step, but it requires a little bit of, let's say, going step back again, right? So we go back into this into the definition of G, and we say if we derive this term here on both sides with respect to G, then we would have something like, well, this thing is, we would have something like that the gradient of G of eta times the integral h of x exponential eta t u of x dx plus, so this is the product rule. We have to now derive the other one. This is g of eta times the derivative of this one is h of x times exponential eta u of x times the inner of that, which is just u of x dx equals 0. Right? What we do here is we say this is, we derive this on both sides, right? The derivative of 1 is 0. So this means that this should be 0, which again means that this should be minus that one. Now we can divide this again. We write this like minus 1 over g of eta times g of eta equals this here. Right? And now we do another trick. We divide this by this, right? This thing goes here, and we note that that 1 over this thing here, 1 over this thing here is the same as g again, right? So let's write this first. In the first step, we say 1 over g of eta gradient g of eta equals, let's call this, I don't know, a 1 over a times what remains here on the other side, e of exponential eta transpose u of x times u of x dx. And now the only observation that we have to do is that 1 over a is exactly the same as g again. All right? So this is nothing else than g of eta times that. Okay? Which then means that what we have here again, g of eta, can be pulled into the integral, and we have q. Right? So this is q then. Right? If we now put g in here, then this is the same as the integral of h of x of g of eta of exponential eta t u of x times u of x dx, which is the same as integral of q of x times u of x dx. And this is the same as the expected value of Q, of U under Q. Right? This is our way we write this. This is our Q, which is the no, this is the general description. This holds for any kind of distribution under the exponential family, right? We didn't put any other assumption on that, right? This is a general Q. This works for every distribution in the exponential family. We can say that the gradient, the log, let's say, yeah, the expression of this here, the gradient of this normalizer here divided by the normalizer itself here is just this here, right? So if you have this expression here, exactly, I write it down here, 1 over g of eta times gradient of g of eta minus is equal to the expectation of u of x under q. And this is nothing else than what we had before. Where is it? Let me. I might have done a mistake there. Where is the log on? Log of g of n. Ah, sorry, of course. Yeah, the gradient of the log is of course 1 over g of n times the gradient of itself. Right? This is just applying the chain rule to the logarithm. Right? This is the same as minus gradient of log of g of eta. And why we do this? Well, we derive first the log, which is 1 over g of n, and we take the inner derivative, which is just the gradient of g of n. I hope I don't. Right? So this is just, it's a little bit because you go in the other direction, right? We want to express this thing here in a different way, and we note that if we derive the negative logarithm of g of eta, right? This is a derivative here, the gradient of it. We apply chain rule. So we first derive the logarithm, which is 1 over g of n, and then we take the inner derivative, which is the gradient of it, right? So we have another expression, a more general expression of the negative gradient of g of eta, right? Which is nice, because now we can say, to find a good, to minimize the Kl divergence, what we have to do, we have to find the Q so that the expectation over it's called the sufficient statistics, right? This is a term that defines you uniquely the parameters that you need for your distribution. For the Gaussian, this is just x and x squared, which is just the mean and the variance here, right? But this is detailed. So what we have to do here is we have to, they call this match the moments of these two distributions. We have a Q distribution and a P distribution. And to find the Q that minimizes the Kl divergence, we only have to find the moments of P and set them to Q. Right? Use the Q that has the same moments as P. This is the whole trick of it. It's right. For the Gaussian case, it's easy, right? If you explain that, if you do this for the Gaussian, you just plug in u of x equals x squared, and you will find out that the expression for the Gaussian is just a particular case of the exponential family where u of x is just that vector. That means if you assume, for example, everything is Gaussian, then you take a u that looks like this, and you just have to match the moments between P and Q. So what you do is you compute mu and sigma of P, and then use a Gaussian that has exactly this mu and this sigma. The Q function that you find out is just another Gaussian with the same moments. Right? This is called moment matching. Yeah. Now, this is the general description of the algorithm, and I'm just showing through the steps. So we assume we have another factorization. This is our factorization here, and we are interested in the posterior again. Again, we want to have the probability of our parameters given our data, which is expressed using this term here. We have 1 over the probability of the data. Of course, it's just applying standard rules here, right? If you multiply with P of D on the left side, then we get exactly this expression here. We assume we have a factorization over this expression. That this is our factors here. And now we use an approximation Q to that P here, right? We have other factors, F tilde, that are normalized again. And for every factor here, we have another factor of F tilde here, which we'd like to optimize. And again, we do the same trick as before. We do this in turns, right? We loop over all factors. And in every instance, in every iteration of our algorithm, we find another factor F tilde so that the Q is very close to the P in terms of the Kl divergence, but now the opposite direction of the Kl divergence, right? So what we aim to minimize is this thing here now, right? We have this is our aim here, right? And now we would like to find a Q. This is our Q that is very close to the P, right? In terms of the Kl divergence, right? And we do this again in turns. We just go over all factors, find the factor so that this whole thing is closer to the actual posterior P, right? This is the individual steps here. First, we're given this joint here. We approximate the posterior. This was said already. The first step is we initialize all approximating factors here. We need some initialization. We also, once we have the initialization of the factors, then we can already compute the posterior approximation Q, which is simply the product of all factors, right? Once we have the factors, we just multiply them up. And now we have a loop over until convergence. We first choose one factor, one of these m factors that we have, which is choose factor number j. We remove the factor from Q by division, right? This is a very interesting thing here. So we have a whole factorization here over all these factors given. We remove that one factor, and we get another distribution here, right? And we denote this other distribution of Q not J, right? This is Q, which is the same distribution as this, consisting of all the factors that we have, with the exception of the particular factor that we have right now. This is called the cavity distribution, right? And now the trick is to find a new Q new that minimizes this Kl divergence here, right? We have now, of course, what we can, sorry, that's one step kind of missing here. This is the cavity distribution, and the trick now is to multiply at the true factor, right? A true factor that we actually know from this distribution here with the cavity distribution, which is this here, and normalize it, right? Then this thing should be very close, or now we should find a Q new that is very close to this thing here, right? And this is done by moment matching, right? We can now assume that we find the moments of this thing here. This is easy to compute, the moments of this thing here. Then we take the moments and create a new distribution under the assumption that we are in the exponential family, for example, Gaussians, right? We can have another Gaussian Q new here, which has the same moments as KL, right? Including the 0th moment, which I'm not talking about here right now. So the Zj can be equally computed, just taking, this is just a normalizer here. And then we evaluate this new factor just by now again from the new function that we just get here, which is our new Gaussian here. We now can divide our cavity again and normalize again, right? We now the normalizer, and voila, we have a new factor, right? This is the new factor that we get, and we can now do this over and over again until we have done this for all factors, and can also do this multiple times for every factor, right? And in the end, we'll have an approximation of our posterior in terms of factorization. Some properties of this algorithm here, there's no guarantee that the iterations will actually converge, but in general, this works quite well. So I have never seen an example where this doesn't converge, at least in the implementations that I'm working with. So I can really recommend this algorithm. This is a theoretical thing here, but I don't think this is of much importance. But I'm not sure about this. I'm just myself very convinced about this. So in contrast to variational base, we have there we have a guarantee that in every step we do not decrease the lower bound. Here this can happen, but in general it's well not so much a problem. The other big difference between variational base and EP is that EP minimizes the other direction of the Kl divergence, and this is just a visualization of what happens or why is this a problem. If we have a multinomial, if your P distribution that you would like to approximate has many peaks, right? For example, this is a mixture of Gaussian here. The blue one is P and the red one is Q. So if the blue one has many peaks, like in a mixture of Gaussians, then minimizing this Kl divergence would give you one big estimation, one big Gaussian in this case, that is kind of in the middle of these two, which is not very nice, right? It's not a very good approximation of P. It would be much better to have something like this here, where we have either one minimum here or the other minimum there, right? And this is obtained using the standard variational approach, where you minimize this Kl divergence and not this Kl divergence, right? This is the drawback of EP. EP does not work well with mixtures, right? But if you have cases, and in particular in the case of Gaussian processes, you have unimodal distributions, then EP works very well. So EP is particularly used for Gaussian processes, and I'm probably showing this also in some other lecture. This is just another comparison. We had this, I think, already. I think when we talked about Gaussian processes, we talked about the so-called Laplace approximation. This is the red one. Yellow is our original distribution, which is not Gaussian, right? We don't know anything about it. And the idea here now is to find a Gaussian approximation to that yellow shape here. One idea was the Laplace approximation, which is red. Another one is the variational method here, which is the green one, and the expectation propagation algorithm is the blue one. And it's hard to say which is best, but I personally prefer the blue one because it's more like, it's kind of closer to the to the actual distribution, right? It's a bit more shifted towards the center, right? Towards where the mass is here, the center of mass is. So it kind of resembles a little bit better the actual distribution than the Laplace. Yeah, and next week we will apply EP to the clutter problem. I'm not showing this here now. I'm just summarizing this. So variational inference I have shown that as an approximation of functions that the Kl divergence is minimal. I said this, I think, a number of times now. We have two algorithms. One is the mean field or variational base. Let's call it better variational base. We have factors that are optimized sequentially by taking the expectation over all other variables, right? We take one factor out and do the expectation over all the rest. This is the whole idea of variational or of Bayesian inference. For GMMs, for the particular case of GMMs, we can reduce the risk of overfitting because we use a fully Bayesian approach. We take the priors into account, right? We not only take a maximum likelihood as we did this in EM, which makes estimation much more robust. And we have seen another algorithm which is called expectation propagation, which minimizes the reverse Kl divergence, right? And we see this, it works using moment matching, right? Moment matching is a very is the key element of the expectation propagation algorithm. Yeah, and we assume for EP, we assume that the factors are in the so-called exponential family. Okay, that's it for today. There's no questions. Thank you.